Hello again. Today we're going to be talking about the stress-strain curve. Now, the stress-strain curve is a relationship between stress and strain in a deforming material. In most mechanics problems, you're going to have some set of variables that are kinematic, that are associated with just the motion, some set of variables that are force-like, and then a set of relationships between those two variables. So for example, when you're doing dynamics problems, the displacement-like or kinematic variables are displacement, velocity, acceleration, angular position, angular velocity, angular acceleration. And there's an internal set of relationships that tell you how to find velocity from position, etc. And then there are the force-like quantities, which are force and moment. And then to relate those two quantities to each other, you have the kinetic relationships in dynamics, basically Newton's law, which tells you that the force is equal to mass times the acceleration, and then you have the rotational version of Newton's law. Now, in strength of materials, we have displacement-like quantities, which are strains. That's displacement per unit length. And then we have force-like quantities, which are stresses, which is force per unit area. And the stress-strain curve expresses the relationship between those two, and that's material dependent. And one of the wonderful and interesting things about the world of strength of materials is that depending on the material that you have, depending on the temperature that you're operating at, depending on the rate at which you're operating, whether it's a fast deformation or a slow deformation, you can get a huge variety of types of relationships between your stress and your strain. So by necessity, I'm going to constrain the discussion for today, this little introduction, to engineering alloys deformed at a moderately low temperature. So room temperature for most engineering alloys is considered a low temperature, and deformed at reasonable rates of deformation. So something that you might see in a lab tension test, for example, a few inches per minute, not impact and not something that might take months or years to deform. Okay, so moderate deformations, low temperature, and the class of materials we're going to consider is engineering alloys. Now, for that set of materials, the stress-strain curve that you're going to see, that you'll see in your book, and you see if you do an experiment, say a tension test in the lab, has several distinct regions to it, which we're going to talk about today, just by way of brief introduction. And then in a subsequent video, we'll do an example that actually uses the information you'll see represented on a stress-strain curve to solve engineering problems. So what are the regions in this stress-strain curve, and what do they actually represent? Well, the first thing that you'll see in a stress-strain curve is a very steep rise in the stress with an increase of strain. And that steep rise is typically initially linear. And that's because nearly all materials, when you deform them just a little bit, behave elastically, which means that the materials deformation is fully reversible. If I apply an elastic load, if I apply a deformation and the material is behaving elastically, the load will rise. And then if I let it go back to its original configuration, the load will go back to zero. Or conversely, if I apply a load to the material, it will deform. And then I remove that load and it goes back exactly to its original configuration. That's elastic deformation. So the slope of that elastic portion of the stress-strain curve is called the Young's modulus. We usually use the symbol capital E to denote that, and that's very important in design calculations. Whenever you do beam bending calculations, when you calculate the loads that arise in, for example, axial compression of the material, you can calculate those loads based on the elastic modulus, that Young's modulus. And of course, that Young's modulus is closely related to other moduli in the material, such as the shear modulus, which you would use to calculate the loads and torques in torsional or shear deformations of the material. So that's the first portion of it. It's the linear increase in the stress with strain, and it's a steep portion. Now, the elastic deformation of the material typically is linear until the material starts deforming plastically. Okay, so that's not true for all materials. Some materials have a nonlinear elastic response. Perfect example of that is rubber, for example, which will have an elastic response, which is not just a straight line. In other words, when I start pulling on the rubber, if I measure the force versus the displacement, or the stress versus the strain, engineering stress versus engineering strain, it'll be linear at the beginning of it, but then it has a very complicated shape. It'll bend over, but it's nevertheless elastic, meaning that if I remove the load, it will go back to its original configuration. It's just not a straight line all the time. So the top of that elastic stress-strain curve portion is designated in a couple of different ways. One of them is called the proportional limit, which is to say that you take a look at the beginning of the stress-strain curve and you put a straight line ruler on that stress-strain curve portion, and you draw a straight line. When the stress-strain curve deviates from the straight line that you've drawn with your ruler, that's called the proportional limit. And that's one measure of when you're exiting the linear elastic region. The other measure that you can take a look at is called the elastic limit, and that's the stress that you can get to before you start experiencing something other than elastic deformation. So the stress that you have to get to, for example, to plastically deform the material. Now, in engineering alloys, the proportional limit and the elastic limit are pretty much identical. In some other materials, that's not necessarily true. Okay, so now once you've reached the limit of the elastic deformation, the material has gone as far as it can go and still be fully reversible deformation. If you remove the load, it goes back to its original configuration. Then something else happens, and that something else depends on the material, and actually it can be different for different kinds of engineering alloys even. If you have, for example, a mild steel, what will then happen is that you will get a region of plastic deformation where there's an upper and lower yield point that's indicated in the stress-strain graph, and essentially you're beginning the process of plastic deformation, which is to say permanent, irreversible deformation, where after you've deformed the material, it no longer returns to its original shape. But the stress is not rising during that little portion, and there's some cool things going on the inside of the material when that's going on. Essentially, flaws in the material called dislocations, linear flaws in the crystal structure of the material, are breaking free from point defects which are binding them. So that goes beyond the scope of this discussion, but let's just say that the stress kind of jiggles around at the point near the top of the elastic portion of the curve until all of those dislocations have been kicked loose, and then you start a region where you get strain hardening. And strain hardening is essentially a process where by plastically deforming the material, you make the material stronger. Now that's pretty cool actually when you think about it, because what it means is that you can actually improve the mechanical properties of a piece of metal just by deforming it. You don't have to put any alloying elements inside of it. You don't have to change the temperature on it. All you need to do is deform the material and it gets stronger. It does this by an accumulation of dislocations on the inside of the material. Again, that goes beyond the scope of this class discussion, but you can experience this personally yourself. If you buy a little piece of copper tubing from the hardware store, and maybe you've done this because you wanted to repair a supply pipe underneath your bathroom sink. So you buy a little piece of copper tubing from the hardware store, and when you initially bend it into shape, it's pretty easy to bend into shape. But then let's say you discover, oh no, I took it to the left and actually I want it to go to the right and I have to bend it around this other object. And now you continue to deform that plastic tubing. The more you deform it, the harder it becomes to deform the tubing. In other words, the tubing is becoming stronger and harder during the process of deformation. On the stress-strain curve, that's reflected by a rising stress as the plastic strain continues to increase. Now, that was the description of what you would expect to see in the stress-strain curve if you had a mild steel sample. If you had something like, let's say, a copper or aluminum specimen, you would still have the proportional, straight line, elastic section of the stress strain curve, you would still reach the top of that elastic portion of the curve, which marks the limit of elastic deformation and beyond which you get plastic deformation. And then you would get yield. In other words, the material starts deforming plastically, but you don't get that little squiggly area of the upper and lower yield point that you would see in steel. You would go straight into the strain hardening section of the stress strain curve. And the definitions of when you have reached the point at which the material is deforming plastically, it's no longer elastic. There's many definitions for that. So for steel, you could pick the upper yield point, the lower yield point, or you can use what's called the offset definition, which is probably the most commonly used definition of yield in materials. And that is to say that you're going to define the stress at which the material deforms plastically as the stress you have to get it to, such that when you unload the material, you have 0.2% residual permanent deformation left in the material, or 0.1%. So depending on whether you use 0.1% or 0.2%, that would be the 0.1% or 0.2% offset definition of yield. You can also use the proportional limit, the stress at which the stress strain curve deviates from being a straight line, but that's a much more sensitive measure of yield. It tends to be conservative, and it tends to be not as repeatable as the offset definition. So the most common definition of yield that is used in engineering practice is the 0.2% offset definition. And if you want to find that on a stress strain curve, the way that you would do it is you would, on the strain axis, you would take a strain of 0.2%. So in other words, a strain of 0.002. And then you draw a straight line from that 0.002 strain up parallel to the elastic portion of the curve. Wherever that straight line intersects the stress strain curve, that's your definition of yield. Now, as the material is continuing to deform, the engineering stress, which is basically a measure of load applied to the specimen divided by original cross-section, will increase as the material strain hardens until it reaches a maximum. And that maximum is called the ultimate tensile strength. And that ultimate tensile strength is basically a measure of the largest load-bearing capacity of the material. It's the largest engineering stress that the material can take before it starts localizing, necking. And at that point, the stress drops off and the load-bearing capacity of the material drops off, and eventually it will fracture. So from the elastic portion, you extract the elastic modulus or Young's modulus. From the 0.2% definition of offset, you can extract the yield strength. The yield strength is important in determining what the allowable stresses in a material are. So if you're designing a building or you're designing a car frame and you don't want it to deform permanently, you want to ensure that the stresses that the frame encounters are going to be equal to the yield strength divided by some safety factor. So divided by a factor of 2 or divided by a factor of 3. And then from the maximum of the engineering stress strain curve, you can extract the ultimate tensile strength. And in general, you don't want to get anywhere near the ultimate tensile strength in your designs because that represents catastrophic failure of the material. So in the next video, what we're going to do is we're going to do an example problem where you use some of these properties that you can extract from the stress strain curve to solve some real problems.